This is the crash scene investigation talk. So we're just going to kind of go over different scenarios where HotSpot is known to crash and kind of what some of the user addressable ones are and what you can do about them. So self-introduction, I think a few of you have been in some of my earlier sessions, but my main job is fixing HotSpot bugs. I've also done some evangelism stuff, co-wrote one of Japan's WebLogic books and a tweet blog. Yeah, that's me on the left in the picture. And today we're talking about crashes. So, why as an end user would you want to hear anybody talk about crashes? Like, why is that your problem? Well, we want to be able, when the JVM crashes, to hopefully identify the root cause, prevent future occurrences, and maybe even if we're not going to be debugging the issue ourselves, know what kind of information our JVM vendor would be interested in so that we can collect everything that's needed before it gets overwritten or deleted. So JVM crash, just to define all our words, sometimes people use the phrase crash kind of in a generic sense of any time a process stops or bails out because something went wrong, they call it a crash. But here I'm being very, very specific, and I'm talking about when the JVM process terminates abnormally. So in the POSIX world, that would be it received some sort of signal from the OS letting it know that it was misbehaving, or maybe it internally detected some sort of inconsistency that it did not feel that it could recover from. And in that case, it will die. So this is basically a native level manifestation. So if you just have some sort of exception thrown that wasn't caught in the JVM exits, that's not a crash in the definition that we're using today. So I get asked this very often, is all these bad things that can happen inside the JVM. Well, why doesn't the JVM do a better job of trying to recover from these situations? And that's not really an ideal response to most of these problems. And that's because when we don't really have confidence in the internal state of the JVM, anything could happen. And anything could happen is a really bad situation to be in when you're dealing with your production data. So a fast fail behavior where we identify that something went wrong and we try and recover from it as quickly as possible is preferred to just trying to go with something where the behavior's consistently is not consistent or is undefined, because that's also a very dangerous situation to be in. And the idea or the thinking behind this is that instead of just having one single point of failure where if something goes down, you have out time, is that you want to cluster your instances in some sense. So your continuity of business is maintained by having redundancy across multiple JVM instances, ideally, as opposed to just putting all your eggs into one basket. So when you do have a crash, there's a few steps that you want to make sure that you take. Obviously, you want to collect any data before it goes away. Sometimes, core files don't delete themselves, so normally you don't have to rush too quickly. But we have come across cases where there have been crashes, and before we could go in and collect the needed information, for whatever reason, it was either overwritten or removed. So if you do want to try and get to the root cause of a crash as much as possible, you might want to go in and archive or back up the information and make sure that it's available for later investigation. And then, of course, just restart the JVM process. We're all engineers, so have you tried restarting it? Is as we know, the answer to most problems. But the idea is that you should go through this process, these beginning steps very, very quickly, and then you can kind of take your time to look through the data that you collected and try and figure out, okay, what actually went wrong. So when we talk about JVM crashes, obviously many JVM crashes are not end-user actionable root causes, right? It's only a subset of them are going to be. So obviously a large number of JVM crashes are a result of internal bugs within the JVM itself, and we'll discuss a few of those scenarios towards the end of this presentation, but there's also a lot of other types of crashes that happen that are not the result of JVM bugs, and those are the kind of ones that are the lowest hanging fruit, where even as end users you can very often identify what went wrong and take corrective action on your own. So first off, what kind of data are you going to collect? Well, the thing most people are familiar with, and the most useful thing in many cases, the first thing you want to look at is the fatal error log, or otherwise known as HS error, with your process ID after that. And normally this will end up in your current working directory. You can override that behavior with, there's an error file argument that you can pass if you want to send it somewhere else. And then if for some reason, like say the current working directory of the JVM doesn't have write permission for whatever reason, the JVM will default to putting it in the temp directory. And on Windows, there's also, it'll look for in your environment for a TMP or a TEMP variable that specifies where files would be written. If you don't have any of those available in your Windows environment and you crash, I don't really know what happens. I assume a black hole opens and sucks everybody in, but ideally you'd want to have your temp directory specified. So the thing about the text error log is it's really good for identifying causes of crashes that we've seen before and we know about. It's not very useful for identifying new issues. So if you have a crash and you don't have a core file and you just have this text error log and someone's looking at that, your JVM vendor is not going to have a very easy time if it's something that we've never seen before. So if we're lucky, it's a new issue that's already been found and resolved and root caused by someone else, then an error log might give you all the information you need to kind of find that, but it's not very helpful for identifying new bugs, especially new JVM bugs. One other thing is, especially in the cloud world, people are more and more concerned with security and personal identifiable information and things like that. Unlike a core file, which is a direct dump of basically all of the data that was in the JVM at the time that we crashed, the error log shouldn't really contain any sensitive information. It should basically be safe to hand off to other people or support engineers and things like that. The exception is sometimes people will actually put credential information on the command line. And because the command line is one of the pieces of the debug information that's put out in the error log, sometimes you'll see people's passwords and credentials in there. So before you hand off an HS error file to someone else or someone outside of your company, you might just want to sanity check it to make sure no one has their passwords in there, because we do see that sometimes. So again, this has kind of two main users or audiences for these files. The JVM vendor might look at this and their support staff might say, okay, we know this, we've seen this before, we can guess what happened here. But end users also can look at this and sometimes make heads or tails out of a lot of different types of situations and problems that can be solved on our own. So the point though is that, there's a lot of data in here that won't make sense to end users. And you have to kind of be willing to just look over stuff that you don't understand and kind of cherry pick the data that you do understand or that you are interested in. And if you kind of go into it expecting to understand everything, you can get frustrated because you keep having to look up different things and learn about what are de-optimization events and stuff like that. But there's just a few very choice pieces of information that are very important, and if you kind of zero in on those, even if you don't understand a whole lot about JVM internals, you can very often find out what went wrong in a general sense without understanding the entirety of the file. So core file, of course, is something that we also get very often, and it's just a complete dump of the process. Maybe you might not get copies of the libraries depending on the operating system, but you definitely get all of the data, the live data that was there. Truncation happens very often. This is kind of one of our biggest problems, is that so you get a core file and either you didn't have enough disk space or there was a disk space quota in effect when the JVM actually crashed, or when the core file was transferred between different systems or sent over a network or something, it gets cut off. And so what happens when we get a truncated core file is very often, this is very OS dependent, but the layout in many cases is that the very end of the core file, which has the individual stacks for each thread, which is probably where we kind of begin our investigation of what happened, gets cut off. And so without the stacks, there's really nothing that we can tell about what the JVM was doing at the moment it crashed. So truncated core files, even if we only lose like 10% of the core file, can't you tell something from that? Very often what's left after you chop off the top is not anything that we can investigate with. So you want to make sure when you have a core file that you make sure that the entire file remains intact. For many operating systems and configurations, we don't get core files by default. Like the Red Hat-based distributions are kind of notorious for this, is that, out of the box, they don't have core files enabled. And the thinking behind this is that in a production environment, if you had a system that was just crashing and then maybe automatically being restarted by some sort of, like, say, availability agent or a node manager or whatever, your file system could fill up with core files very, very quickly. And so to kind of avoid that scenario where you have a long-term outage just because of some intermittent JVM failures, or process failures, some operating systems default to not having core file generation enabled. So what we recommend always having core file generation enabled, but if you're concerned about disk space issues, what a lot of people do is they have a separate partition, just like you do with logging, as a best practice, is that you want to log to a separate file system that can fill up without bringing your system down. And the same thing with core files. So if you can do on the operating system side the configuration necessary to make sure that your core files are sent to a non-vital file system, maybe even a remote file system, you can ensure that a whole series of consecutive crashes will not fill up your disk space and bring down your entire system. Also on Windows, we don't, on the client version of Windows, like, the non-server version of Windows, like Windows 10 or Windows 8 or whatever, Java won't put out a mini dump or a core file by default unless you add one of these options. And that option actually changed between 8 and 9. So core file gives us all sorts of information about the native state, the internal state of the JVM, but it also gives us information about the native code that is third party and external to the JVM. So if you're running JNI libraries, or even if you're not using any third-party JNI code, the JVM itself, as just a process running on the operating system, is using libc and all the OS-provided libraries. And so there's a collection of information here that could help you debug JVM issues or native issues. So if you want to look at and actually take a crack at core file debugging, it's obviously beyond the scope of a 45-minute crash course like this. But the easiest way to get into it and to maybe pull some interesting information out of a core file is to look at the Serviceability Agent. So the Serviceability Agent is a tool that until fairly recently hasn't been too well known outside of Sun Oracle, but it's been there for a long time, and it allows us in a platform-independent way to open and examine core files and to pull information out of that core file. So for example, if you were interested in what classes were loaded and you wanted to kind of explore those or look at information from the heap or look at your threads and stuff, the Serviceability Agent, unlike a regular native debugger, actually has baked in information about how the JVM is designed and implemented, and it kind of understands and can parse those native data structures within the JVM. So it's intelligent enough that even if you would have a really hard time with a native debugger with the Serviceability Agent, you can say, okay, well, show me a list of classes that are loaded, and it can just pull that information out for you automatically. So this would be kind of the first step towards digging in further into core files on your own to see what kind of information they contain and maybe what you can deduce from a core file. So other important data, if we're just collecting stuff for analysis later, we really are going to want to have copies of all the native libraries that were loaded at the time of the crash. If we don't have those, then it's very hard after the fact to load a core file in a debugger and figure out, when we're looking at the individual stacks, what each frame corresponds to in each native library. So just getting copies of those libraries is very handy that were loaded, and I'll show you how to get that information in just a second. And of course, you want to check your logs in your standard out and see if there's anything kind of sketchy going on right before we crash. Very often, if we're running out of memory or we've blown the stack or something like that, there'll actually be some errors thrown by the application before we crash as it was kind of struggling to recover, and that can be obviously a very useful clue in our investigation. So I said we want copies of the native libraries if we're going to go digging around a core file to look inside of it. And the way we figure out which libraries were loaded at the moment we crashed is very platform dependent. But basically with Linux, we can open the core with GDB, the GNU debugger, and then run info shared, and that will just give me a list of all the libraries, all the files that were loaded at the time that we crashed. And so then I can just copy all those into an archive. With Windows, there's the list modules command if we're using WinDBG. On Solaris, there's actually this PLDD core file. On most other POSIX operating systems, this would only be work against a live process. But Solaris seems to have this cool thing where there's a whole bunch of the P commands will work on core files in addition to live processes. So like on Linux, you wouldn't be able to do this, but on Solaris, you can actually do this, and that's pretty cool. And then the LLVM equivalent of this is the LLDB tools image list. And there's tools out there that kind of automate this process. At Oracle, we use a script called package app that you just point it at the core file and it will go and it will pull all the libraries that we need to do analysis. So let's jump into what actually causes crash. So one of the most common ones that we see is Stack Overflow. And when people see that, they go, well, Stack Overflow is very common. We don't crash with Stack Overflow. Why would you think that could cause a crash? And the reason people think that is because we're really good at recovering from it like most of the time. And so it's kind of like a seatbelt, right? Like, just because you've gotten in a few car accidents and your seatbelt like saved your life or something, you're not going to be surprised when you hear that other people are less fortunate when they have car accidents. Stack overflows are dealt with and handled okay most of the time, but every once in a while they bring your JVM down. And the reason they can do that, the reason they're so dangerous is because when you have a Stack Overflow, depending on the circumstances, you can just corrupt arbitrary memory in the JVM's address space silently. So there's no hint, there's no indication that this is what's actually happened. And all of a sudden you just have some broken memory somewhere in your JVM, and that will rear its ugly head at some point. So by definition, if there's been a Stack Overflow, the behavior of the JVM is considered undefined until reboot. You should really reboot when you have a Stack Overflow, no matter how benign it might seem or it seems like it was handled correctly. A lot of people consider it kind of an error or a bad design choice to have the JVM continue running at all when a Stack Overflow has been encountered. Stack Overflow is one of the reasons why we handle them so well is if we're just interpreting bytecode in the template interpreter, they're very easy to handle because we kind of know where we are in the stack and we know what the limit is, and so it's very easy to not hit that limit and to bail out when we get close to it. But when we're running native code, and by native code I mean obviously third-party or JNI code or just code that we generated through JIT compilation, it can be very difficult to detect Stack Overflow conditions and to recover from them. In many cases, completely impossible. So what does this actually look like in practice? So just a regular native scenario where we have a thread and the stack for the thread will have a guard page at the end. And this is not HotSpot specific at all. I mean, this is just general, like if you're using the pthreads library on Linux and you ask it for a thread, it'll give you a thread and it'll put a little, by default, it'll give you a guard page at the end of that. And your regular stack will have read, write, hopefully not execute. If you're on 64-bit, you won't have execute on that. And then for obvious security reasons, but the guard page won't have any permission set to it. So the stack pointer, when it touches the guard page, you get your sigsegv and we die and game over. So that's the standard generic thing for really any native code. So HotSpot makes life a little more complicated, but in a good way. I mean, it tries to handle this with a little more elegance. And so what we do is we actually have some additional guard pages that we have that we add to the thread ourselves. So the guard page may or may not be there depending on who made the thread. A thread might be something that the HotSpot internally created because it's just spawning another thread for whatever reason, or the thread might be something that the OS created, or the JNI application that was invoking the HotSpot JVM with the invocation API as an embedded JVM instance might have created. So a thread could come from a whole bunch of different sources. So it may or may not have the POSIX, the pthreads library guard page there, but we don't really need it because we stick our own guard pages in. We have these yellow pages and these red pages. So now when we start running out of stack space, when we touch the yellow page region, what happens is we generate a Stack Overflow error and we temporarily make the yellow page area read and writable. And so that's to give us a little bit of leeway so that we can try and unwind the stack in a sane process and kind of restore operation and not die right there. That said, if we touch the red area, we're out, and it's just immediately game over, and we crash because the red area is kind of the limit where we've accepted that we can't handle this situation, and so it's better to bail proactively. So there's even when we succeed with unwinding from a Stack Overflow, the things are in a pretty bad situation at that point. If we're in the middle of a critical section, meaning that we're holding a lock when that happened, we will usually unwind without going through any finally clause or anything and doing the unlock operation. So very often when you have a hang and you have a whole bunch of threads that are waiting for a lock that just seems, no thread seems to be holding it, like an intrinsic lock, that can very often be caused by a Stack Overflow, because Stack Overflow will unwind even and not do the normal process where we would release the lock as we unwind, because we can't guarantee that the data that we were touching in the critical section is in a consistent state. So it's a kind of a worst case scenario, but we want to make sure that it's better to leave the lock in place if we can't guarantee that the data is in a consistent form as we unwind. But there's even worse scenarios where we can corrupt memory and kind of silently. But when we do it in native code, things are even more complicated, because there's no way to unwind native code. We don't know what it is. It's not code that we generated necessarily. And so there's no way to really know what's going on. So what we do to kind of avoid blowing through the stack when we run native code is every time we transition from Java code to native code, we do what's called stack banging. And stack banging is where we kind of hit, we do a read, a test read, X number of pages further down the stack. And that kind of guarantees us in some sense that, well, if this read attempt doesn't fail, then at least we have this much space. So if I'm going to transition into native code because there's like a JNI call or I'm calling into the JVM or something, I can stack bang, and then this will guarantee me that I have at least some reasonable amount of room to play. So as that goes, then we hopefully proactively hit the Stack Overflow error while we're in Java. Because like I said, when we're executing Java, we know how to unwind those frames. We can walk down the stack because it's our own code. But if we hit this while we're running native code, then it's too late and we're just over. So stack banging can actually, the distance that we bang down the stack can actually be manipulated by the stack shadow pages option, which just tells you how many pages down the stack you want. And the size of a page is, of course, platform dependent. And there's a trade-off here. If you do a really small stack bang, where you're not going that far down, then you're much more likely you lose the advantage of the stack bang in the first place. You're much more likely to see a Stack Overflow error that we can't recover from. If we do it too proactively and we do it way out, then we might actually be getting stack overflows that would otherwise be avoidable. Like in reality, we wouldn't be exhausting the stack, but because we're stack banging so proactively and so far down the stack, we actually end up kind of wasting stack space. So if we're running native code, sometimes we can end up in this situation. If you can see, the stack pointer has actually jumped off the stack. And it goes, well, what's after the stack, right? So pretty much every normal platform, the stack grows down. And so this is somewhere lower in the address space than our thread stack was. And especially if you're on a 32-bit platform, the address space is pretty tight, right? So there's going to be something there. And who knows what's there? It could be the heap. It could be another thread. But we just go in and use it as stack. We corrupt that. And then we can silently return. And this happens amazingly often. It doesn't seem like it should be that possible, because you go, how do you jump over this? Why would you not, trigger any of these? But there's cases with native code where people will have extremely large arrays that they allocate on the stack because I can only assume they're horrible people. And so if you have an array that you don't initialize and you don't touch, but it's stack allocated, and it's X11 libraries is kind of a very common, one of the most common suspects for doing this. If you have a huge array here that you don't actually use, do something and then come back, you can actually mess around with the stack down here without actually touching any of these guard pages. when this happens, so you've basically corrupted memory in your JVM space, address space, and you have no idea what, and you haven't even noticed that a problem's happened. So we can also control the sizes of the red and yellow pages, so we can kind of avoid this scenario. If we have ideally long enough yellow pages and long enough or enough red pages, then we're less likely to have that case where we could accidentally jump over them without triggering them. But then again, there's also a trade-off of how much stack space are you willing to waste to get more safety. And so there's always a trade-off going here. So the rule is whenever there's a stack overflow, there's no such thing as a benign stack overflow. You always want to reboot your system when you have a stack overflow because if you've seen one, there's probably been a bunch. In fact, a stack overflow is one of several types of, they're subclasses of virtual machine error. And if you look at the Java doc for virtual machine error, it very clearly states that the JVM is broken and cannot continue operating. So by definition, by specification, once any of these have actually happened, the JVM's behavior is undefined. And once you've seen one stack overflow, they're kind of like roaches. Like if you've seen one, you're at a restaurant, you see a roach, like maybe that roach got caught, but you're not gonna go back there to eat anytime soon, right? You probably have a bunch. And so if you occasionally see a stack overflow in your log, that might mean there's a whole bunch that you're not noticing and that we're not catching and that are causing crashes. And we've seen this time and time again. So in JDK 8 and later, we actually have in the HS error file, it'll tell you only if there are stack overflow or out of memory errors, it'll give you a count. But just remember that this count tells you how many times we successfully unwound from a stack overflow. Meaning if there was one of those stack overflows that we saw a few slides ago where we just silently corrupted memory and then went back, that would not be counted here. So sometimes people will look at the HS error file and be like, oh, I don't have any stack overflows in here. So a stack overflow could not have been the root cause. And that's not true. It's very difficult to actually rule out a stack overflow because they can happen without leaving any trace that they caused problems. And so if you see this, you definitely need to investigate, figure out what stack overflow happened and resolve that issue. But just because you don't see this does not guarantee that stack overflows are not causing your crash. Here's another really well-known one at this point is the use of internal and private APIs. And I'm not here to nag you guys or anything like that, but I do just kind of want to point this out because we do see this as a very common cause of crashes. So this is the poster boy for this is the SunMISC unsafe, which lets you kind of do all sorts of crazy stuff within the JVM itself with Java directly. It's basically a way of almost kind of doing JNI-like stuff to JVM internals without using JNI. So if anyone's as old as me, I think some of you are, you might remember the 80s we had like the VIC 1001 or the VIC 20 here, and these common machines were very popular, and one of the things that we wanted to do once we kind of mastered the basic language was to start programming in assembly. And the way that we messed around with the low-level internals of these machines and programmed in assembly was using peek and poke, and most basics would offer a call command, so you could jump to an arbitrary address and start executing code. So peek and poke were kind of the key. Like if you can peek and poke, you can wreak any havoc you want because you can read and write arbitrary addresses anywhere in the computer. And SunMISC unsafe is basically peek and poke for the JVM. It allows you to just do anything that you should not be allowed to do. So internally, we've always used it for implementing reflection and serialization and NIO, and all different parts of the JDK class library use SunMISC unsafe, but it was never ever intended for use outside of Sun and or Oracle. So there's code in here to do this, and I mentioned this during, I think, my thread talk, is that I did a whole presentation about why people should never use SunMISC unsafe, and then I put the slides on SlideShare, and someone came to me like half a year later and was like, I learned how to use SunMISC unsafe by watching your by watching your slides, looking at your slides. So I want to, yes, you can do this. Don't do this. Like, please don't do this. Your code will not run forever. bad things will happen. But that said, let me show you a wonderful unsafe demo. So you can see how cool this is.
Can give you 4 more ways to get it.
We don't need more ways to get it. Okay, so let me.
It's kind of like ethical hacking. Oh, here's how you do it, but don't.
So, oh, am I really doing this again? Sorry. I had a horrible blow up in my last section with demos. So I'm praying to the demo gods to be kinder to me this time around. Can people see this font? So, okay, so I'm gonna run first my unsafe demo. That's basically just, actually, let me show you what this is, what this does here. So this is really straightforward. We basically just, I say get the fire and then play with the fire. So we're using one unsafe method called getInt, and we're trying to read a null pointer. We're dereferencing a null pointer, so this is obviously not gonna go well, but let's just, in order to beat a dead horse, show you that, so we crashed here. So, I mean, this kind of breaks an invariant that's in people's minds that if I'm writing in pure Java, I shouldn't crash. And that's just not true. If you're using internal APIs, there's all sorts of ways that you can get into trouble and break things, and tons of frameworks do this. And it's okay when they make no mistakes, but no programmer out there is perfect and never makes any mistakes. So this is why SunMISC unsafe is so dangerous. But here it's pretty, you open up a HS error log and you see this and you're like, well, this looks pretty sketchy, right? Like unsafe getInt, you're not gonna spend too much time wondering what happened if you see something like this. So let's look at something a little more interesting. So I have another really short example. In fact, I started writing this by cutting and pasting the previous one. So again, we get the fire. But this time, playing with the fire means that I'm taking an object field, and what should be an object field but isn't, and I'm writing some junk to it. And then I call GC. And so what's happening is this field is actually supposed to be an object pointer, right? This is what the field is. So this should be a valid pointer. It should either be null or it should be pointing somewhere into the heap. But here, I'm writing not a heap pointer there. And then I call system GC and just like, good luck with that. Let's see what happens. I mean, you all know what's gonna happen, but let's just. All right, this time we crashed, and we're crashing in GC, right? We're actually running compaction when we crash. And you can look at the rest of the HS error file, but there's no indication in the HS error file that SunMISC unsafe was responsible for this. This is where the real danger is because you corrupt memory, and then the root cause happens after the fact, and then after the fact, you crash. And the code you crash, you could look at this and go, well, the GC must be bad. There must be a problem with garbage collection. And it's no, arbitrary memory corruption is horrible because there's a really loose connection between the root cause and you crash. Some indeterminate amount of time will pass, and it's very hard to trace things back to figure out what caused the what caused the crash originally. All right, where is my? So here I've demoed the awesome power of unsafe. So I mean, lots of people say, well, isn't flexibility a good thing? Like it's, most of us know that, if we behave and, we don't use that, we're gonna be safe. But people that want to, we should let them. Why isn't that a good thing? And I'm gonna definitively say no. Or at least, okay, not always. And the reasoning here is that it's not, if you're just writing your own code and you're doing, your simple little project, then that's fine. You get whatever you deserve. But if these are used in open source components that are kind of spread all over the world and used by all these millions of people, most people that get burned by unsafe usage have no idea what unsafe is. So it's used by third-party components, whether commercial or open source, that they just happen to depend on for their application. So if there's some way to know that you're using unsafe, then that maybe the conversation would be different. But unsafe is kind of like this landmine that's just sitting in your code base or in your stack, and it can come out to bite you in unexpected times. And when it does come out to bite you, it's very hard to get to the root cause of it. So obviously Jigsaw, one of the goals is to try and eventually close this loophole. It's not currently closed, just because so many frameworks actually use unsafe still, but we're slowly migrating methods out of unsafe to kind of get rid of this stuff. So moving on, native code obviously can cause crashes because native code can do whatever it wants. It's kind of like unsafe on steroids. But just say, when I say native code, I'm not just talking about third-party native code in JNI. In the JDK itself, we use a ton of native code. And so if you look at like the class library, we've got almost 1 million lines of straight C and C++ code in there that gives us the class library. Most of that's actually in client GUI stuff and code and things like that. So it's almost as much as HotSpot. So there's a ton of native code, and if there's a bug in any of that code, it can bring the JVM to its knees. But that said, this code is pretty darn stable at this point. And so usually when we see JNI crashes or crashes resulting from native code bugs, it's generally third-party code. Not all of the crashes, but most of them are. Actually, most of them seem to be from a Minecraft, but that's a different conversation. So native code, I mean, the real problem with native code problems is that to effectively debug them, you have to have the skill set for that particular platform. It's not enough to even just like know C or know assembly or whatever. Like, you really have to be familiar with the operating system and the debugging tools for that particular platform, which many Java developers don't have. The whole idea of Java is that you don't have to know the intimate details of every single platform that you depend on, but JNI code kind of takes that advantage away. So as always, it's a trade-off. Now, one thing you can do is there's an option called xcheck JNI, and what that does is that sanity checks some of the interaction between JNI and the JVM. So, JNI code, if it's native code, it can do whatever it wants. It can write to arbitrary addresses. It can just blow things up. It can call abort. You can't stop it from really ruining your party if it wants to do that. But a large subset of JNI problems actually stem from misuse of the JNI API itself. So there's a well-defined API where it says your JNI code, if it wants to interact with the JVM, so if it wants to instantiate a new object, or if it wants to call a method from the JVM, it calls back into the JVM. And when it does that, if it passes the wrong arguments somehow, that can mess up the internal state of the JVM itself. For performance reasons, we don't sanity check the arguments on every single call because that would bring the JVM down to a crawl. But if you are having problems and you're having crashes and you're running third-party JNI code, one of the things I recommend is to run with xcheck JNI, and that will kind of you'll have a performance hit, but it'll sanity check all the JNI invocations. It won't find all JNI problems. It won't even necessarily find most JVM problems, but there's a large subset there that it will help you catch, and that's handy sometimes. Another thing that happens very commonly with JNI code is it will install its own signal handler. So if you look at the HSError log, it'll actually tell you for each signal. I only have 2 of them listed here, but there's a whole bunch of them that always get listed, about 10 of them in the HSError logs. And it'll tell you where, like what address basically each signal handler that's been registered points to. And so we can see right here that this points to, if there's an illegal instruction signal, then the JVM has registered a handler to handle that. If we see something that doesn't look like the JVM here, that should stand out, and you should be like, wow, we should really try signal chaining here. We should do something because this will prevent the JVM from handling these signals the way it was designed to. So we have something called signal chaining, which is a way of basically interposing between native code and the operating system to basically say, so if native code tries to call sig action to register its own signal handler, the HotSpot signal chaining implementation will remember what it tried to register, and then when that signal handler is actually called in the future, the HotSpot signal handler, this HotSpot signal handler will look at the source of the signal, and by source I mean look at the instruction pointer. That the signal will actually tell you, where the instruction pointer was when the signal was triggered. And so we can look at the instruction pointer and say, okay, this was in code we own, or this is in code I don't know about. If it's in code we own, we take care of it. If it's code we don't know about, thank you, then we just pass it along to the third-party one that was registered. So lots of cases, if you see a handler registered that you don't recognize and seems strange, try signal handling, and you can do it just by preloading the libjsig library. This is in the same directory as your libjvm. And by preloading this will kind of interpose itself between and this is obviously just for POSIX platforms, but it'll interpose itself between the native code and and the OS's signal handling stuff. So memory exhaustion should be pretty straightforward. Just want to point out that generally it's more of a problem on 32-bit platforms just because the address space is so confined. Even like on Windows, I think it was like 2 gigs, which is ridiculously small these days. But even on 64-bit platforms, there's lots of layout issues that you can run into. So you have this inexhaustible address space, but you can still, just because things are in the way of each other and they can't grow the way they want to grow. This seems, for whatever reason, to happen more often on Solaris than perhaps other platforms, but it is something to be aware of. My coworker Poonam, that's tomorrow. Okay, good. So it hasn't happened yet. So you can go see getting rid of error messages from my coworker Poonam, and she talks a lot about native memory stuff. And she also did a talk last year about troubleshooting native memory leaks in Java applications. The slides are available online. I haven't found a video of it, but it's an excellent presentation, so I highly recommend checking that out. Corrupt bytecode. So we have a really quick demo here just to show you what bad bytecode is. Bytecode, if it's broken, we have a verifier that's supposed to catch those mistakes and stop bad things from happening, and that will protect you. So normally you should not crash if you have bad bytecode. But if you disable the verifier, you can crash, and you can crash in very unpredictable ways. So here I have class A. It has this do something method that takes 3 integers and then adds them together. I have class B that takes 3 Java lang integers. It takes 3 objects and then adds them together, right? And then I have class C that extends class A. And then I have a demo that basically instantiates the class C and then calls do something on it, right? So C, because it extends class A, this should be the implementation that gets called. So this is what it looks like in the object graph. C currently extends class A, and everything just works, right? But let's say we change this. We change that to class B. So it was extending class A, but now it's extending class B. But we only compile class C in isolation. We recompile just this class and not all these classes. If we only recompile just C in isolation, then what happens is, well, the verifier actually goes, hey, you've got broken bytecode. That's not going to fly. Okay, so that's really good. But if we're like horrible people and we do xverify none here, then we crash. And what's important is when we crash, it's not clear at all what the root cause was. There's no this was broken bytecode or whatever. So it gives you these very difficult to troubleshoot crash scenarios. So always, always, always leave bytecode enabled. Because it's just, people think of it as a security thing and they think, well, I trust all my code, so, I don't need it. It's not just for security. It protects you from mistakes that all developers make during the development process, especially when you're mixing libraries from all sorts of different stuff. OS issues, we have a lot of operating systems will corrupt the SIMD XMM registers. They don't handle the save restore operations correctly. We've seen this at least 4 or 5 times with Linux kernels over the past 10 years. And that also gives you just these crashes that basically corrupt arbitrary memory, because when we spill stuff to the XMM registers and then bring them back, we get completely different values. And of course, finally, we have JVM bugs. This is kind of the most obvious cause of crashes. And we have these kind of issues still because there's always a performance stability trade-off. It's like the more risky stuff we do, the better performance we get, but the more likely we are to get burned. So a basic way to think about these kind of things is that, well, why don't I make things simpler? Like if I have a reproducible crash and I'm using G1, why don't I use a simpler GC and see if it reproduces with that? So if you kind of back away from the riskier, higher performance options, you can say, well, maybe, I don't know why that's white in the center there, but you can, kind of narrow down, well, if you take everything back to serial and you're still crashing, then it's probably not a GC bug. And it's probably, it's probably something completely unrelated. But, by scaling back the complexity, you can kind of, troubleshoot in that sense. And obviously, JIT compilation, C2 is more complicated and more risky than C1, which is more complicated and risky than interpreter. So by dialing back the, which you can use like tiered stop compilation to stop tiered compilation at C1, for example, if you want to, or you can just disable JIT compilation altogether and just run with the interpreter with XInt. But these are ways that you can use to kind of tell that you have a JIT issue. There's also, when you crash, as a result of a JIT compilation bug, there's actually 3 different scenarios where you can crash. You could crash while you're JIT compiling. You actually crash in the JIT compiler, and that's what we're looking at here, where it's actually the compiler thread that is crashing. You can crash when you're running the JIT compiled code. So if you see here, when you look at the stack, you get these nice helpful things that just are impossible to read in this color scheme. But the capital J here is compiled Java code. And you see that this is compiled Java code, and we're crashing while we're running this. So maybe this code was compiled incorrectly. So maybe we should disable compilation of this. And then there's other JIT crashes where we just corrupt memory because the JIT code we emitted is garbage. And so when we run it, it doesn't crash, but it breaks something else in the heap or something. So you can disable JIT globally, or you can use a compile command to just disable JIT for a particular method that you think might be triggering a JIT bug. So, and always just if it's a JVM bug, try the latest JVM. So thank you very much. Most JVM issues that we get from like the java.com bug database and stuff actually are one of these issues that I've covered. And so there's stuff that you as an end user can actually troubleshoot and diagnose on your own. And that can save you a lot of time and hassle as opposed to maybe having to deal with your JVM vendor or whatever. So thank you very much. I appreciate your time.